Okay, good morning. I hope I am audible and my voice is clear. Okay, so we are going to start in 2 minutes. Uh, Let us wait for some more participants to join and then we will start. Okay, so let us start and let me hide this. Okay, so should we start? Okay, great. So yesterday we had sessions on fundamentals of AI, machine learning, and deep learning. And in session one, we discussed various terminologies related to AI, machine learning, and deep learning. And then in the second session, which begins with the foundation of neural network-based models, and you have also uh, gone through the uh, hands-on sessions on CNN model on one of the sample dataset. And towards the end, you have seen various applications of AI. So yesterday's session was basically fundamentals of AI, which is the prerequisite part for generative AI. In today's session, the overall sessions that are scheduled today are based on generative AI, and we are going to see some of the fundamental foundational models in generative AI in session number 2, 3, and 4. And we are going to have a hands-on session as well on one of the generative AI model. In session one, from this session, you can expect what the preliminary information and terminologies and a brief idea about generative AI and the model exist and the fundamentals behind generative AI models. and the different types of generative AI models, and what are the challenges and the applications that are there. So overall session is uh, in the overall session, we are going to start with the introduction of generative AI, how it is different from discriminative AI models, and the type of generative AI generative models that are there, and some of the basic concepts that are when you are going to attend other sessions where particular model will be discussed of generative AI. So these terminologies you will come across many a time. So what is the latent space, what is the generative loss, and the loss functions that are used in generative AI models. So I will be covering those basic concepts so that in the upcoming sessions, you will have understanding of those terminologies. And then we are going to see some of the applications of these generative AI models, the challenges that are there with the existing models that we have, and all the generative AI is basically is used to create new data in terms of whether in terms of text or image or video. So when we are dealing with different types of data, particularly two types of data like text and images, what are the challenges and what are the characteristics of those data is there, and how understanding of this type of data helps you to understand the generative AI models. And then, though those models are going to cover in the upcoming sessions, I'll give you a brief idea what are those generative AI models and how they generate new content. And towards the end, we are going to end up with some of the research questions that are still open to solve. Okay, so let's begin with what is generative models. So at their core, basically generative models are AI models that are designed to create new data samples that resembles to the data that were trained on. So the generative models, basically the models will create is designed to create samples of images or any type of data, and the distribution of that data should resembles the training data it provides. For example, let's say if you train a generative model on an image of cats, it should be able to generate new realistic cat images that were not in the original data set. However, they are similar to the training data set that is on which generative AI model trained. So to understand this, let's think about a simple function y is equal to f of x, where x is your input data and y is the output. So in AI or machine learning and deep learning that we have discussed in the yesterday's session, you have come across different types of machine learning or a deep learning problem where the y could be a category that you predict based on some input data, or it might be a number output based on regression problem, or it could be predicting probability. So in traditional machine learning, when uh, the output is a number, discrete value, or class or probability, then they are called discriminative AI. So we discriminative models. So we are dealing with discriminative models. However, when the output is a natural language, text, image, or audio, video, then we are dealing with generative AI models. Generative AI, it is, though it becomes popular nowadays, but it is not something new. You might have indirectly or directly come across through generative AI models where, for example, sometime you want to convert your uh, text into one language to another language, for example, Hindi to English or English to Hindi or some other language. You might have used a Google translation on the Google where you paste it and it converts into the second language, which is an example of machine translation task, which is also basically a generative AI model. So, however, the popularity have begun when the recent LLM based models have comes into the picture. So basically, discriminative model, if you are saying, so it focus on predicting some label y given some input x, and it is not generating a new one. And the whole focus of discriminative model is predicting the label given some input. So usually expressed as p of conditional probability p of y x. For instance, a discriminative model might look an image and predict whether it is a cat and dog, or it might look a text whether this text is text belongs to, let's say, news article, and it can predict whether it is the news is fake or real. Whereas generative models, on the other hand, learn to underline the data distribution, let's say denoted by p of x, that represents the probability distribution of the x. And in the previous session, yesterday, we have discussed uh, the overall idea of generative AI is to learn the distribution of the data. For example, if you're working with an images, this p of x might represent the probability distribution of pixels value that make up that particular image. Once the model learns this distribution, it can generate a new data. So generative AI, generative models and discriminative models plays a complementary role in AI, where while generative models generate new uh, samples that resembles the training data, discriminative models are created tasks like classification or regression. So you can think of discriminative model as a judge that categorize the data, and generative models as an artist that create new data. So if we go through the history of generative model, it was started with simple probabilistic models such as Gaussian mixture model that basically assumes that the data is can be represented by the combination of Gaussian distributions, and it was started with those basic fundamental probabilistic model. However, as we have seen in the previous session also yesterday, that these models have a limitation in handling complex and high dimensional data like images and text. Uh, then there is in 2013, variational autoencoder, in short VAEs, were introduced by Kingma and Welling. So this variational autoencoders uses neural network based architecture to learn the latent representation of the data, and that enables the generation of new samples. And that was the first significant step in generative AI, which have been used to generate new images. For example, this variational autoencoder might be trained on a handwritten digit, could generate new digit like handwritten images. And then there is another significant step when GAN architecture, generative adversarial network, was proposed in 2014 by Ian Godfellow. So Ian Godfellow is one of the researchers that have a popular book on deep learning. And so if you want to study deep learning in detail, you can refer that book, one of the popular book in. Sorry, so shifting from the topic. Okay, so Ian Godfellow has proposed this generative adversarial network, where unlike other networks that or other models that we had discussed so far and we are going to discuss, generative AI, generative adversarial network, or simply GAN, works in an adversarial setup, and it's more of like combination of two networks that play against each other, and the overall objective is to train generator so that it can generate new images. And then diffusion model comes into the picture in 2015, which generates data by gradually denoising the random noises. And these models have been becomes quite popular recently, like tools like stable diffusion for image generation. So until this, most of the generative AI models were focused on generating new images or videos and so on. However, when in 2017, when transformer comes into the picture, then uh, generative AI started to become popular in text generation tasks. Because earlier, the pre-trained models that we were using was more intuitive to use in image related tasks or computer vision tasks. However, the introduction of transformers uh, enable to use pre-trained language models in natural language processing tasks. So from there, the journey of GPT models and other models that uh, you are now interacting with have become popular and have been using the pre-trained language models. So this history we had discussed yesterday in the first session of Introduction to AI, and so I'm skipping this part. So the overall objective of generative model is to learn the underlying data distribution, which is P of X, which describes the probability of observing a particular data point. For example, in an image, this might mean learning the distribution of pixel value that forms the realistic image. And for in case of text, it might be learning about the probability of word sequences that forms the coherent or natural sentences. And once the model learns this probability distribution, it can generate a new sample that look like they have come from the same distribution as the training data. So basically, the we want to model, we want to we want the model distributions denoted by P model X to be as close as the possible to the true data distribution. And this process is also known as density estimation. So when we talk about data distribution, so data distribution is basically, in case of images, it could be pixel value distribution, or in case of text, it could be word sequences that forms a natural text. However, there is a challenge in that because in real world, the data distribution are often high dimensional and the complex that as we have discussed in the last session. And because even a simple image, you might have a millions of pixels, and to learn the distribution of those and that a particular image, basically the learning the relationship between the pixels among in an image would be a very complex task. So even this image shows that complex two-dimensional distribution, whereas in case of high-dimensional data, it could be far more complex. So that distribution can be can be high dimensional and complex in case of real world data. So simply we cannot just learn the simple distribution. Okay. So till this point of time, we had discussed what is generative AI and how it is different from discriminative AI, which we had discussed in yesterday's session. Now, so the whole idea of generative AI models was to learn the data distribution. And all the models that are there available in generative AI can be broadly classified into two categories based on how they approach the learning the data distribution. And based on the learning approach, they are divided into two types. Yes, I'm coming on to that. So all the existing models can be divided into two types: explicit density estimation and implicit density estimation. So when we talk about explicit density estimation, we basically explicitly define a probability distribution function first, and then train our model and train that distribution function directly on the training data. So that have two categories. So basically, explicit density estimation, we define the data distribution explicitly, a function we define, and we train over it. That explicit density estimation again have two types of categories: traceable density estimation and approximate density estimation. So in traceable density models, where the distribution can be computed exactly on the data. So, and there are various models in these categories like neural auto density estimation model, masked auto density estimation model. One of the popular is pixel RNN, pixel CNN, and other. Whereas uh, in approximate density estimation, because the computation of probability distribution on high dimensional data is computationally intensive. So instead of this, some of the models, what they do, they approximate the probability distribution of the data into simpler or standard probability distribution model, probability distribution like Gaussian or some other. So instead of exactly calculating the probability distribution, these model approximates. And we have categories like variational autoencoder and Boltzmann machine. However, in this category, uh, we define our function. For example, let me give you an example of pixel RNN, which is one of the model in traceable density estimation. What it does, it uses chain rule to decompose the likelihood or the probability of an image into a product of one-dimensional distribution. So basically, in pixel RNN or pixel CNN, we define likelihood of an image, or probability of an image, as a product of probability distribution over the pixel given previous pixels. So here X represents basically pixel value. So in pixel RNN, you define probability of ith pixel given all the previous pixels. Now, and that the product of this is basically your distribution of an image. So we explicitly defining a function, and when we define a function, you can see there are two things that we need to keep in mind. One of the important thing is how we are going to define which pixels are the previous pixels. So we need to define the ordering of the pixel. So that needed the ordering of the pixel in this particular model. So that ordering we need to define what and for example, let's say uh, this is an image, and this is first pixel. If we start from top left, so this is the first pixel, and the previous pixels are no pixels. And if we generate the next pixel or learn about calculate the probability of this pixel, the previous pixel might be this. So one of the way to ordering of the pixel could be starting from top left to going to the right bottom. However, this uh, complex distribution over the pixel values usually represented by the neural network to capture this complexity, and we need to define the ordering as well. So this is how pixel RNN defines the probability distribution function, and then this uh, distribution is, or likelihood is, basically maximized on the training data. So then during the training we maximize the likelihood of the training data. So though I hope it is clear what is explicit density estimation. So we define a function and then we train over the training model. However, there is another category called implicit density estimation, where the whole idea is not to define a function, rather than uh, somehow train our model so that it can just sample the data, whether it is an image or text, which is similar to the training data. So here, one of the popular model comes, which is called generative adversarial network, which comes under direct method, which basically generates samples through a generator network without defining the distribution explicitly. So throughout this first session, I am just giving a brief of those models. In the upcoming session, you are going to see one of the two popular models called variation autoencoder and the GAN. You are going to see the working of these models in depth, and you are going to see how they works and the hands-on on the GAN and the variation autoencoder. So implicit density estimation, you do not focus on defining the explicitly defining the p of x, but instead try to learn to sample from it. It also have a Markov chain method like nice and glow, which uses invertible transformation to map data to simpler distribution and then sample from it. However, popular models are GAN, variation autoencoder, pixel and CN. I hope now it is clear what is explicit density estimation and implicit density estimation. So are we good here? Is it clear to this point of time? If you have any query, you can write it on the chat. Okay. There are some other models which uses combination of explicit density estimation idea and the uh, implicit density estimation, which okay. So though there is no exact scenario or the case where you can pick which one to use. However, if you think the data distribution is 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 highly complex, or your data is quite high dimensional data, then instead of going to using explicit density estimation model where you are defining a product distribution function, uh, better is to use uh, implicit density estimation models like GAN to generate data, because explicitly defining a function like pixel RN and pixel CNN, they are quite slow in terms of training and generating new data, because they define a function, and over the pixel they have to define the ordering of the pixels. So learning the probability distribution or learning the likelihood of the image is also slow, and the generation is also sequential, so those models generate one pixel at a time. Whereas implicit density estimation model like GAN uh, can generate faster compared to pixel RN and pixel CNN. However, there is no overall yes and no answer for this. Uh, it depends on which type of data you are training and how the model can work on which type of problem. However, one of the criteria could be the dimensionality. If you have high dimensional data, and then it's better to go with the implicit density. Some other models, like recent one, uh, like diffusion models uses both explicit and implicit density estimation model, where it learns to generate data by denoising the random noise, which combine the interpretability of explicit density models and flexibility of implicit model. So uh, this diffusion model is also you are going to see in day 3, where you are going to see no, day 3, day 4, where you are going to discuss about recent multi-models that are there. So you are going to see in this detail in upcoming. So now, till this point of time, we understood two things. What is generative AI? Types of generative AI models. Now, in the upcoming sessions, you are going to see one in sessions you are going to see those models in details, and during those models you are going to find out some of the concepts, some of the related terminologies which will be used quite often. uh, so directly going to those sessions, I thought let's give you intuitive idea of those uh, terminologies. One of the so to understand this, let me give you a layman idea of one of the model called autoencoder in deep learning. So you have understood about the. So this is not a generative AI model. This is one of the deep learning model uh, which have two networks. One is the encoder and one is the decoder. In discriminative AI and CNN model or machine learning models, you have seen that okay, so you give X input to the model and model predict some output, and from the training data where you have the ground truth value, which is the actual output, you define a loss function, and then you learn by training the model is basically you try to minimize this loss. This is what you have uh, studied in the yesterday's session. One of the model which is encoder and decoder model, so autoencoder is take X as an input, and this could be a neural network architecture where some input layer and the hidden layer and one output layer is there, which generates an output, could be a vector, and this vector where each value represents each each value is a number basically, and this vector is given to the decoder, and decoder tries to again reconstruct the same image. So fundamental difference between this model and other models that you have studied like CNN and other is that we are not it is predicting again reconstructing the same image. And how this model is trained, so you uh, define a loss function over the predicted output and the actual input. So we are not using any y here. So it reconstructs the same data. It could be an image. Let's say this is an image, and this is again the reconstructed image. So loss is defined between the difference between the created image and actual image. So again, intuition that if you see here, the encoder encoded the input into a vector representation. And during the training, this model is trained to minimize this loss. By minimizing this loss means that the reconstructed image is as similar to the original image. And once this training is done during the backpropagation using gradient descent or any variants of gradient descent, once the model is trained, it means that this vector, which is actually uh, output of encoder, is a representation of that image. So the image which is in raw form have n dimensional, high dimensional pixels value, pixels. It is compressed into a single one dimensional small vector. So that means that this, if the model is trained and the reconstructed image is as similar to the original image, it means that the vector that we are giving to the decoder is basically the representation of that image. I hope it is clear. And why I have shifted to autoencoder, just so this is just an idea how autoencoder works. And once it is trained, because now we have a compact representation of an image, this, what we can do, we can drop the decoder. Vector is the feature vector of image. You can say this. You can say this. This basically represent that image, and hypothetically you can think of each value of this vector as showing some properties of an image. For example, let's say this particular starting this value might be describing about skin tone. This might be describing about eye color and so on. So hypothetically, these different values are showing the properties of this image. And this compact k-dimensional vector is basically in k-dimensional space. This particular k-dimensional vector is representing that image. So for all training images, you might have different vectors in k-dimensional space or in a space. So you can say this is a feature vector. In terminology, this is called latent vector. And this collection of all the latent vectors in that high dimensional space, let's say the dimension of vector is k, then you can call this space as a latent space. So that means that in the latent space, each vector is representing one image. So now you can think of various application of it. So for example, let's say uh, I have a huge data set of images. However, my memory of storing those images is small. So I want to compress all those images. So what you can do, you can train an autoencoder model where after training, you can just drop the decoder and you can use the encoder to just get the vectors, and you can just save this vector instead of saving this high dimensional data, because these vectors are also representing that image. Also, you can use for the classification task as well. Let's say you want to building a model that predict cat and dog. So after training, you drop the decoder and pass this vector to any uh, discriminator model. Let's say either you can pass to a sigmoid layer, which is predicting cat and dog, or even you can use decision tree, SVM, or any machine learning model, even the logistic regression to predict the cat and dog. So this small representation basically representing that image. So the intuition of some of the models in generative AI comes from there. Though this is not a generative AI model, let me tell you, because here we are not generating new data. So this is not generating new data. It is basically the vector is representing one of the unique image in the data. And the property is that using this data, what you can do, you can basically generate the same image again, but not the new. However, some of the basic concepts from there have been used in generative AI, and now we are going to discuss about that. This part was basically background of what we are going to discuss now. So each latent vector is basically a discrete vector representing one particular data uniquely. However, uh, in case of generative AI, so now if I say latent space, now you all know what latent space is. Yes or no? So in latent space, so now in case of generative AI, uh, we want the latent space as a space where which is a low dimensional representation of data, which encodes the complex data into simpler pattern, and it decodes output from this complex compressed mapping. Okay. And so this the low dimensional representation is called the latent space representation. However, when we move towards generative AI, the latent space, which was the discrete in nature in case of autoencoder models, here in generative AI, we need uh, this model should have properties like continuity. So instead of discrete, it should be continuous in nature. So, for example, image with a million of pixels can be encoded into much smaller set of numbers in the latent space, capturing its essential features, right? Just like we have discussed just now. Then model can decode and reconstruct the original data from this latent representation. This idea have been used in one of the generative AI model called variational autoencoder, which is trained on the faces. Here in case of generative AI, this latent space might represent the features like eye size, nose, shape, or skin tone. In case of, let's say, we are taking an example of faces in a compact form. And once we learn this latent space, by sampling any point from the latent space, the model can generate new face. Unlike autoencoders, where uh, all those compact vectors are discrete in nature, in case of generative AI, this latent space should have three properties. One is the continuity, that is the point closer together in the latent space should produce a similar output. For example, uh, we had a vector that representing an image, and if we just tweak that vector, we change particular value, let's say eye size from 0.5 to 0.8, that should uh, generate a new face with a change in the eye size, and the change should be slightly, not drastically, so that there is continuity we need. And there is one property called completeness, that from the latent space that is continuous, whenever we pick any new data anywhere in the latent space, it should generate a meaningful content, unlike with in autoencoders where it is not possible. And disentanglement, which says that each dimension in the latent space should control a distinct feature. So for example, in a sample from this latent space which represented by a vector, this particular dimension shows one particular property of the image, this and so on. So each value represents one property that controls a distinct feature. For example, one dimension might control smile intensity, another head pose, which allows precise manipulation. So I hope you understood what is latent space, and in the upcoming sessions, you might heard this terminology again and again. So latent space or latent vector. So vector is one of the point in the latent space, and basically those are the feature vector, you can say, of it, hidden feature vectors of the image. Another important thing is the reconstruction. So because we want to reconstruct the input like data from the latent space, and if we are just tweaking some of the one of the latent dimension, you can see the smile manipulation in the image is happening when you are tweaking one of the point in the latent dimension. Similarly, another example shows the pose manipulation by varying another latent dimension. So there comes two types of loss. To ensure that we want to generate a data which is similar to original, we use reconstruction loss, and usually most of the time it is mean square loss, which ensures that the generated data is similar to the original data. And basically, this MSE measures the difference between the input and the reconstructed output. And there is another loss called generative loss, which guides the model through balance the quality. So how realistic the output is, and how diverse is the output is. For example, one of the model that you're going to see in last session, which is GAN, the generator loss comes from the adversarial game between the generator and the discriminator, which ensures that the generated samples are basically both are high quality and the diverse in the nature. Okay, so taking a pause, I hope till this point of time everything is clear, and at least you have intuition of what is latent space and the latent vector, and what is the requirement in case of we are talking about generative AI. And in just immediate next session, you are going to see how variational autoencoder trained to learn that latent space. Okay, so coming to how you're going to train any generative models. So training a generative models involves a pipeline. You start with the data and feed to the model and compute a loss and then optimize the model parameters. However, this process comes with various challenges like high dimensional data, like images or video, and computational cost of training those large neural networks. And usually to optimize this model, we use techniques like stochastic gradient descent or other variants of gradient descents, like Adam and all, which iteratively adjusts the model parameters to minimize the loss using backpropagation. And the choice of loss functions in generative AI models is one of the crucial tasks. So sometimes, usually in different models, like one of the loss is reconstruction loss, which measures the difference between the output image and the actual image or actual data. And one of the loss that you are going to see called scale divergence loss, which is used in variational autoencoder, which ensures that the latent distribution that is learned is as close to the standard distribution like Gaussian or, or other to make the sampling easier. So you might have heard about cosine similarity, or You can say that. So in case of autoencoder, you can say that both are doing the reduction in dimension. So autoencoder, yes. So one of the application of autoencoder is could be the compressing the data. So yes, one of the application is similar to the. However, autoencoders have been used in various other tasks as well. Where uh, Manhattan distance or other distance matrices you might have uh, studied about, where you calculate the distance between 2 points. Uh, Kale divergence, and there is another divergence called Jensen-Shannon divergence, known as J's divergence. These two divergences are basically, you will find out in various models where these two divergences have been used, and these divergences basically measure the difference between two probability distributions. So let's say you have two probability distributions, P1 and P2. So there's that to measures the difference between those two probability distributions. And the scale divergence laws have been also used in variational autoencoder to check whether the learned latent distribution is whether it is closed enough to the standard distribution. So this is one of the terminology that one of the laws that we use. Adversarial laws we use in GAN, where you train two models that compete with each other. So you use two types of laws, loss with respect to discriminator and loss with respect to generator. Okay, so this point of time, what we had discussed again, what is generative AI? Types of generative models, basic concepts like latent space, latent vector, also some loss losses that use in generative AI. Now, once you learn, so suppose you have learned the latent space of the data. Now, so how you are going to sample from it? So sampling means taking one latent vector and generating a new data. So once you have trained, so their generative models usually produce the new data by through sampling, and this can be done via different types of sampling, like random sampling, where you randomly pick point from the latent space as an input latent vector, and you can give this to decoder part in variational autoencoder, which generates a new image. Or you can use ancestral sampling, where generation of an image is done step by step, similar to the pixel RNN, where you generate a pixel value based on the previous value. So you generate the pixels in a sequential manner, where each pixel is sampled based on the previous ones. Or there is another way of sampling called Markov chain Monte Carlo, which is in short MCMC, which iteratively refines the samples to match the target distribution. For example, in GAN, which is trained on the face, you might sample a random vector from the latent space and pass it to the generator to produce the new image. So, in summary, we any one of the generative models try to learn the latent distribution, which should be in continuous, and a sampling should be realistic from that latent space. And to generate new data, you sample from that. And most of those models are focused on these points. So all these generative models have wide range of applications that are transforming industries, academia, and so on. For example, you have a stable diffusion model and del E, which generates the realistic images such as photorealistic faces or landscapes or any surreal images for the art or the game assets. For example, this stable diffusion can create a landscape which looks realistic. And so this one example is shown the landscape generated by the Sora, which is an OpenAI model, which model is proposed by the OpenAI. There's another application called speech generation, so text to speech, voiceover and dubbing, and which looks real. And I would suggest you to go this website, 11 Labs. Uh, Unlike most of the text to speech uh, models where the output of the speech, output of the text, or output of the audio looks mechanical, this particular model, this particular uh, company which have used the generative AI to give you the realistic human-like text-to-speech conversion, where you can change the tone, you can change uh, the way it should generate the output. And there are some others. Video generation, you have OpenAI's Sora that you can go Google View 3, and this can create high quality videos for different purposes you can use. Text generation is another application. I hope you all are aware with the Chat GPT, where it uses GPT models that generates human-like text for question answering, story writing, or even you can uh, use for the code generation. And nowadays, students are using for doing their assignments. There is another application of important application of these generative AI models for data augmentation or synthetic data generation. Most of the time, when we are dealing with any critical machine learning task where we need huge amount of data, however, the data is not available, then these models can be used to generate synthetic data, which is similar to the original data, uh, and this synthetic data can be used to train a complex model. And there are some other applications like creative AI, and in science you have uh, different applications of this generative models. Now we are going to discuss about challenges that when we train these models, uh, what are the challenges and what are the terminologies related to those challenges uh, that you are going to see in the upcoming sessions. So one of the problem with generative AI models, particularly in generative adversarial network, the output that it generates, it does not generate a diverse output. For example, here this example is shown for the mode collapse problem in GAN, where in MNIST dataset where you have digits, handwritten digits from 0 to 9. However, this model is generating few of those uh, images. It is not covering from 0 to 9 all the digits. So model generates limited variety of output. So there is when model loses the diversity, then it is called the mode collapse, and it is commonly seen in GAN, and that you are going to see in the. And there are various solutions have been proposed, modifying the loss function, augmenting the input of generator network with some conditional vectors, and so on. So this is one. So this is one problem, mode collapse. Another one is the training instability, and this also might usually seen in GAN models where uh, training the GAN can be unstable, where model might not converge. So when we say convergence of the model, we says that the loss of the model is minimized to optimal value. So model is not converging, and there are or there are other problems like vanishing gradients. These are the things that we are going to see in the upcoming. So training as instability is another issue. Uh, there is another problem with generative challenges in generative AI, that in case of classical machine learning models, you usually come with the evaluation matrices. For example, if you are using classification task, you can use precision, recall, accuracy, and so on to check whether your model is accurate enough or not. However, in case of generative AI models, evaluation matrices is 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 one of the challenge. Which evaluation matrix you are going to use, and there are some current matrices have been proposed like FID and inception score. So FID means fresher inception distance, and inception score assess these two basically assess the output quality, which is the image quality, and one of the matrix called perplexity, which is used in case of text, and these two use in case of images. Again, this you are going to see in upcoming sessions. So because quality model quality is qualitative measures, not quantitative. So how you're going to assess whether your model is generating good quality output is again challenge. Another one is ethics. This is one of the most important challenge in nowadays, where use of generative AI have been misused to create deep fake information, spreading misinformation. So earlier, when somebody have to spread a fake news or fake information, it has to manually write and then post it. So it might take time. But nowadays, you can use any GPT models or any text generation model just to write some fascinating story or some uh, any misinformation. You can just take it from those models and you can post it. So for example, here there is one example shown here where we asked ChatGPT to suggest a product. Okay, so there is one question. Uh, what is it? What if to check quality we use? I mean, that depends on the task. You can use uh, these techniques as an evaluation matrix as well, apart from other matrices. So here we deliberately asking the ChatGPT to suggest a product description for selling a customer to drink high in sugar, which is not in healthy. However, we are asking to write a product description uh, to health conscious customers such that they don't focus on too much on the sugar content. So we are manipulating the uh, product description. So this product description can be copied and post over the product description website, which basically misleading the information. So misleading information can be created. Deep fakes you are seeing. Also, you uh, most of the participants are teachers, and they might be facing challenges from the students. Whenever you give any assignment, you nowadays you usually find out the 90% or maybe more than 90% are written using ChatGPT, and sometimes it even they are not uh, giving efforts to change the style, font, or even so that it should not look like it is generated from ChatGPT. There is as it is copy from there and submitted. So there are some open areas to mitigate or those challenge related to unethical practices like watermarking and explainability. However, still it is one of the problem. Biasness is again issue with the generative models. So if generative models are trained on one particular type of data based on uh, one particular race or one particular demographic area data, uh, it will generate data of the same type. So you might have a biased training data, you might have biased model design, and that may lead to unfair outcomes. So some mitigation approach like using diverse data set, which again a challenging task to collect data from different sources, and some fairness constraint you can apply. And another crucial issue with those generative models is privacy concern, where model memorize the training data and there could be sensitive data leakage, and there are some solutions like instead of using original data, we can use the synthetic data to train the model. And one another issue, environmental issue, that you have high computational cost in case of generative AI. So you all those GPT models are basically generating high carbon footprints because there is high resource demands like GPUs and TPUs. So there is another area of research which is focusing on coming up with the efficient architectures and reducing the model sizes so that the carbon footprint can be reduced. So you can see here the carbon footprints of those GPT models are increasing day by day. Okay, so now till this point of time, we discuss what is generative AI, type of generative models, some of the key concepts, terminologies within generative AI, and some of the models, some of the challenges, and how the training is done in generative AI. Now, for now, we are going to discuss about challenges with respect to the text and images, because both uh, type of data differ significantly due to their distinct characteristics. And generative model with respect to these two type of data differ due to the difference in the characteristic of this data types. So taking a 1 minute pause, and meanwhile, if you have any question, you can write it on the chat. Then we'll start again. So basically, okay. So one question was surreal. Surreal means the real. I mean, and okay. So this okay, fine. If you have any other question, you can just write from the chat. Otherwise, in 1 minute we will start again. Hmm. Okay. Now, regarding the type of data, when we talk about text, uh, text is usually uh, discrete in nature and sequential. For example, line which is written there, for example, I like this movie. This text is in sequential in nature. So for it might be seen that this particular uh, word depends on the previous words. So text is intuitively uh, sequential in nature, and the words in the text usually represented by a word vectors, which is also known as a word embedding. Whereas in case of images, images are continuous in nature and high dimensional. Consists of pixel grid. We have pixel grid as shown here. So data represented by a pixel grid. So, so model uh, for text generation often uses autoregressive models like transformer, where uh, each point of time, for example, the student open there when it is predicting the next word. So it checks for the probability of, let's say, book, given all the previous word, the student open and there. Similarly, checks for probability of laptop, given all the previous word, check for probability of exam. So it generates uh, or it predicts the next word based on the previous words given as in a context. So predict next token given the context. Context means the previous words. And for example, for in case of images, model like GAN or variation autoencoder diffusion models, they map the latent vectors to the pixel grid. So you come up with the latent vectors that are sampled from the latent space, and they map to the pixel grid, and they generate an image that ensures the coherence with respect to spatiality and visual quality. Whereas in case of uh, text, model generate coherent sequence, basically the natural sentences. So in case of if we talk about in terms of latent space, text models basically capture the semantic meaning through the word embeddings, where each sentence, for example, the same uh, student open their book. The student is represented by a word vector, and open is represented by a vector, and there is represented by the vector, and so on. So this basically together called the word embeddings. So through the word embeddings, the models captures the semantic meaning of. Whereas in case of images, the latent space basically captures the visual features like shape, color, and so on. For instance, if we consider an image model, one latent dimension might control the brightness of an image and so on. Loss functions also differs. In case of text, usually text model uses cross entropy loss to measure the sequence likelihood, whereas in case of image, we use reconstruction loss, such as in case of variation autoencoder diffusion and adversarial loss in GAN, which basically measures the quality of the images. There are different evaluation metrics as well. Throughout those sessions, you are going to see those uh, evaluation matrices. In case of text, you have perplexity. You have a blue bilingual evaluation understudy, which captures where two texts are similar to each other. RUG is the recall-oriented understudy for existing evolution, and for image, you have different types of square to capture the image quality. There are different challenges as well compared to text and images. In case of text, there is a long-term coherence or long-term dependency among the words need to be captured, which becomes one of the challenge in case of text. Factual accuracy is another challenge, and obviously it is computationally expensive and bias and ethics, which is common to both text and image. Whereas in case of images, most of the generative AI models face challenge of non-convergence, mod collapse, and so on. Okay, so I had already discussed about type of models. One of the models is variational autoencoder that you are going to study in the next session. So I am skipping this uh, discussion of these models because these models you are going to discuss, we are going to discuss in the next session. Adversarial training, generative GAN model, which is you're going to see in the upcoming session in detail, is uses two types of network, generator and discriminator, where generator generates an image and where discriminator checks whether the image is fake or real or not. And those two models compete with each other. And towards the end of the learning, the whole idea, the whole objective is to train our generator so that it can generate realistic image similar to the training data. So it uses an adversarial setup. It is more of like a game between the generator and discriminator. There are the diffusion models. Again, you are going to see in the conversation where model training happens via incremental noise addition. So initially, noise is added to the images, and then denoising step is done to image generation. And during this process, models uh, able to generate the new samples as well. So these models basically adds the noise to the data incrementally during the training and learn to reverse this process by denoising. One of the model is called stable diffusion, which generates high quality image from the random noise. In case of text, you have transformers, which which trains on the next token prediction via self-supervised learning, which uses self-attention mechanism, and we are going to see in details in upcoming sessions. And each model have their unique strength and it making them suitable for different tasks. There are lots of applications of generative models industry. In case of technology industries, you have AI assistants, code generation softwares, advertising. Generative AI have been used for content creation, healthcare, banking, chatbots, and fraud detections, and so on. Similarly, in education, personalized learning and content creating uh, for this generative AI models have been used. There are some research questions which can be picked up as a problem statement for in generative AI field. One of the research is improving stability and diversity, reducing the computational complexity like training time and inference time, and addressing some of the ethical challenges like biasness, alignment, and the deepfakes, which also comes under that ethical AI. Okay, so these are the future scopes coming of the multi-models that can take multiple type of data and real-time generation and real-time translation, hyper-personalization like adaptive learning and emotional intelligence, domain-specific models which uh, can be created for particular task, autonomous agents that can take decision on its own. So this is an idea of generative AI. So this session was mainly focused on giving you the introduction of generative AI. Now onwards, whatever we had discussed briefly in this session, you are going to see those models in details and the implementation of those models in details. So day two, we had covered the introduction of generative models. In second session, you are going to see variational autoencoder, which is one of the generative AI model in detail, how it is trained and how it works, and you will have a hands-on on building variational autoencoder in Python language. And in the last session, you will see generative adversarial network in detail with the mathematical intuition behind it and the variants of the GAN and how it works. So that covers the today's session coverage. Day three is purely focused on the text generation part. So generative AI in text, and then next day four and day five will be focusing on different parts of the generative AI. So this is so if you have any question, you can ask. We have 5 minutes. Otherwise, this session is over, and we are going to have uh, generative AI models in detail in upcoming sessions. Thank you. If you have any questions, you can write it on the chat or you can unmute yourself and discuss. Okay, so that is the end of first session. We are going to start our second session after a short break around 11:15. Meanwhile, I am available here as well. So if you have any questions, you can just drop it on the chat.